Okay, good afternoon to all. Welcome to this contact hour number 28. Okay, so today is the final uh, uh, class related to the syllabus that we'll be covering. Okay, next class will be on review. So this is the final class, and in this class we'll discuss some issues in classification. Okay, and so those issues are some problems with classification and some other important topic. And after that we will discuss about the assignment, because a lot of you are asking about stuff there, and you are not able to, some of you are not able to either see how to start working in those files and folders, or getting some problems while using the folders. Okay, so we will discuss that after we have covered this part in classification. Okay, and then we will discuss in the second half of this session. I will discuss about the assignment. Entirely it will be on assignment. I'll give you a lot of hints, so just wait for that time. Okay, so tomorrow there is no class scheduled, so next class will most likely be next Saturday or Sunday. Okay, that is a review class, so it is better if you have a review just before the exam, and that is what will happen, so it is good for you. Okay, all right, so let us start with one very important issue that should be taken, that should be kept in mind while performing supervised learning, such as the classification. Okay. And that is called the problem of overfitting. Okay, so a lot of classifiers such as decision trees, okay, KN, and all these classifiers, they suffer from this overfitting problem. That is, in simple terms, it means fitting too much to the training data. Okay, so remember that the objective of training data is to learn the pattern, right? So the classifier learns some patterns from the training data and to generalize it, and it should be able to generalize it. That means if it gets a new data that is not present in the training set, it should be able to classify that correctly, right? Or classify most of the unseen data correctly. Okay, if it doesn't happen, then there might be a problem with the overfitting problem. Okay, so what it means is that you are fitting. So if you are getting very good results in training data, right, that is, you are performing cross validation and all, and you are getting very good results there. Okay, but or you are getting good results while you are performing any, say, splits and training split and test split and getting good results there. But when you see an entirely new data, test data, then the results are not good. Okay, so that is where the problem of overfitting might be present. Okay, so there is a question: in most of the models we used only train and test data, but we never used validation data. Can you please clarify? Okay, so validation data is a part of training data only. Okay, so test data is kept separate. I've explained this multiple times. So test data is entirely separate. Training data is further divided into a training part and validation part. Okay, so that you can improve the accuracy, right? If you use the complete data for training, then what will you test upon? During training, you should look at certain examples and should be able to see how you are performing, how your classifier is performing, right? So that data that is used during training, okay, for validation, it's called validation set. Okay, so from the training set itself, you put some small part as validation set. Right. So that you will again look at the result of the validation set. What is the output? How much accuracy you are getting? And based upon that accuracy, you will again further tune your parameters. And then once you are sure that okay, you have got good score, then you will once only test on the test set. Okay, but you have not done this part because uh, that is quite a different thing. Okay, you are not supposed to right now, but when you do machine learning and all these things, when you go to that level, then you will be able to. Then you should be doing this. Okay, right now you are only learning basics, so you're not done that. Okay, right now what we have been doing is cross validation or train and test. Okay. But that is important. So it's, if you take an analogy of that, it is similar to how a teacher might evaluate students, right? So when we give you some practice problems to solve, okay, so we teach you something, so you learn something. So think of yourself as a class buyer, okay, uh, just in a very loose way. And when we teach you something in the class, we might give you some problem to solve, right? And then ask you what it is. We might give you hints. Okay, so that is kind of validation. So you are validated whether you have learned or not properly. Okay, but when we want to test you, will will be an EC1, EC2, all these things, right? Midterm exam. In that we separate only one field give, and we will evaluate final accuracy, how much you have learned based upon the test that you are giving, right? Midterm or end term. But the practice problems, all those practice we are performing, that is also testing something, but it is during your learning phase. Okay, so think of it as that analogy. Okay, I think that is a good analogy to think about training, validation, and test. So test is your exam, final exam. Validation is kind of your homework or assignment or during the class, whatever we are giving you, some problems to think about and uh, evaluate yourself. Okay, so you keep on practicing until you feel confident that okay, now you have learned something, right? So you'll keep on revising some topics. If you have not learned some concepts, you'll revise it and again evaluate yourself. Once you are done, then you say okay, I'm ready for test, and then you go and give a test. So that is your final test evaluation. Okay. So the problem with overfitting comes because uh, you are the classifier is learning too much, or it is learning too many patterns from the noise, maybe from the data set, from the training data set, or maybe it is learning from, or maybe the data set is not sufficient. Okay, so it's kind of uh, so it is biased, or it is going too much towards the training data, so it is kind of fitting too much into the training and it's not able to generalize better. Okay, so there is a very famous diagram for that we will discuss. Okay, and we will discuss the overfitting problems in terms of decision trees because they are easy to visualize and it's a very common problem in decision trees. Okay, and the assignment also has you'll see that you'll have to set something, some parameters to avoid overfitting kind of stuff. That's called pruning. Okay, and we'll also discuss somewhat with an example, with a practical example of that is ensemble based methods. Okay, so this ensemble based methods and overfitting are two topics that we will discuss today. So this is a very famous or popular kind of graph that you will see a lot of times whenever overfitting topic is discussed. Okay, most of the time you'll see this kind of graph when discussing overfitting problem. So what is happening here is, if you look at the, so if you look at this line downwards, okay, so this is showing the training error, the error during training. So right from the top, you can see that the training error is decreasing. So as you make, so it's in terms of decision tree, but it can be similar in terms of other classifiers. They also have certain parameters which, when you increase those number of parameters, okay, maybe the degree of the polynomial or something, you'll see that you are getting very good accuracy in the training set. So this line is the error in training set which is decreasing, okay, or you can say the accuracy is improving as you make the tree more and more complex. Okay, so here the complex means as you increase the number of nodes in the decision tree, maybe you are looking at every example, and creating a tree based upon that example, right, till the leaf node. So for every case in the example set, in the training set, you have a leaf in the tree, and you are actually getting like 100% accuracy maybe, or maybe very near to 100% accuracy, or you can say zero error rate. So here the vertical axis is the error rate. So as the error rate decreases, you can see the accuracy improves, right? So as you increase the complexity of the tree, complexity means as the number of nodes are increased, the error rate will go down, or you can say the accuracy will go high in the training set. Okay, and at the beginning, what happens is that when you increase the complexity, and let's say you have also have a test set on which you are testing, okay, while you are training, and you are also testing on the test set, that is separate. So you'll see that the test error also decreases initially, okay, along with the training error, the test error also decreases. But there will come a time when beyond this, if you increase the complexity of the tree, beyond this, while the training error will keep on decreasing, okay, or you can say while the accuracy in the training set will keep on decreasing, the accuracy of the test set on the test set will start decreasing, or you can say the error rate will start increasing beyond that point. Okay, so there is a kind of minima, you can say, here for the test set, beyond which the error rate will keep on increasing. Okay, so it doesn't matter now, beyond which if you are increasing the complexity, the test error will actually increase, or you can say the accuracy on the test set will then start decreasing until it reaches some point beyond which then it will keep stable, but it has decreased quite a lot as compared to that inflection point here, okay, or the point or the minima here. Okay, and this is happening while the training error still keeps decreasing. Okay, so if you draw a vertical line, let's say this point, and the vertical point on the training set, you can see that the training error is very less, 0.05. Okay, but the test error has improved. It is like a lot of it is 30% as compared to 5% of the error rate in the training set. Okay, so 6 times more. So from equal training and test errors, you have now increased the error on the test set tremendously as you have increased the complexity. Okay, so this is a problem that is called overfitting. Now, why is it happening? It's because in the decision tree, what is happening? You are fitting exactly to the training error. You are not generalizing enough. Okay, generalizing means there should come a point beyond which you should not continue splitting the nodes. Okay, so you should stop sometime when the complexity has reached a certain level. Okay, in case of decision tree, in other classifiers also you have some kind of setting where you should stop. Okay, so and that point is somewhere around this point, this minima point. Okay, that is circled here, the red point. So you should stop somewhere around here. So the complexity should not be beyond this. Okay, so it need not be exact minima point, but it should be somewhere around. Okay, so beyond this is what called overfitting has occurred. Okay, or you are fitting too much to the training set, so that your accuracy on the training set is improving, but at the cost of accuracy on the test set. The accuracy on the test set will actually now go down because you are fitting too much in the training set and are not able to generalize enough. We will say example, a small example of this toy example. Okay, and so this is the point where, so I'll draw in. So this is overweighting has happened here. Okay, and there is one more thing that is called underweighting, even though it is not discussed much, because mostly we will create the classifier with enough complexity. Okay, so but sometimes it might be a problem, and that's called underfitting, when you have not trained enough, or you have stopped before even decreasing the training error by much. Okay, so this is the point, much before the inflection point when the minima is there. So much before that, if you stop creating your tree, it's called underfitting. That means the model is not complex enough. Okay, not trained enough. You have not trained the model enough. You need, in case of decision tree, the training error may decrease further without actually increasing the test error. Okay, so if you stop much earlier, then it's underfitting. Sorry. Okay, but if you go beyond this minima, then the error will keep on, the training error will keep on decreasing, but the test error will now increase. So this is overweighting. Okay, so that is the theory behind it. We will not go into much detail of detailing the theory. Rather, we will just look at one example of decision tree, where we will see, or one example each of two cases in decision tree when the overweighting has happened. Okay, and we will see how pruning the tree or stopping before helps in improving the accuracy on the test set. Okay, because ultimately what matters is the accuracy on the test set. Okay, that will tell how good your classifier is able to generalize to unseen data. Okay, now here you have a training set and test set. So 10 examples in training and 10 examples on test set. So there are two decision trees. So you can see that the top one, the one on top left, is the decision tree which is more complex because it has more nodes. Okay, so as we have seen in earlier, the more complexity means, it might mean overfitting might have happened. Okay, if the complexity is beyond that level, that point of minima. Okay, so let us look at these examples. So let's say these are the two decision trees which have been created by certain method. Okay, and so you have got training set. You created these. Let's say the top decision tree. Let's look at the first decision tree, the one on top. Okay, let's look at the model M1, and say now you are using the test set on this decision tree. Okay, so this decision tree model has been created, and now you are using the test set to see how accurate the results are. Okay. So now please go one by one to these examples on the test set, each sample, and just count the accuracy or the number of errors or number of correct classifications. Okay. So human, let's start with human, and you are looking at model M1, that is the top decision tree, and the rightmost column is the actual class label. Okay, and see whether the classifier is able to, the model M1 is able to correctly get the class. So whatever the first, the human, so name is human. So there are 4 features of each animal here. Okay, or you can say each living being. So what this classifier is trying to do is trying to classify whether a particular animal or a particular living being, whether it is a mammal or not. Okay, mammal or non-mammal. So that is what it is trying to classify based upon 4 features, that is the body temperature, whether it's warm blooded or cold blooded, whether it gives birth or maybe gives eggs. Okay, so it is just gives birth or not, and whether it is 4-legged or not, and whether it hibernates or not. Okay, so based on these 4 features, so they are all binary features. So based on these 4 features, it will label either yes or no, whether it's a mammal or not a mammal. Okay. So this is an example of where you have overfitting due to noise. Okay, due to noise here, and the noise here in the training set, you can see the noise here is represented by the stars. So if there are 2 examples where you have noise. Noise means there is some problem in the data set itself, in the training data itself. Okay. So here the class label are incorrectly labeled. classes are incorrectly given. So bat is written as not a mammal. Okay, so bat is not a mammal, and whale is also not a mammal. So it's labeled as no and no. So there are two problems, two examples that are noisy, or you can say there's some problem in the data set. In this case, the labels are incorrect. Okay, now you are trying to you have created a model based upon this, and that is on the top. That is model M1. So what about human? In the test set, the first example is human. So what will it be labeled as? So start with the root node, body temperature. Now for human it is warm blooded, so it will go left. Then gives birth, yes, it will go again left. And then it is four-legged, and here it is no. Okay, so when it is four-legged, no, the human will be classified as a non-mammal. Okay, so that is one problem you have, the first error. Let's count the number of errors. Okay, so there's already one error you have got for human. So human is incorrectly labeled. Okay, it's not an error. It is an error. Yes, it is a non-mammal. Let's look at pigeon. How will it be labeled? Pigeon, mammal or non-mammal? Warm-blooded, yes. Gives birth, no. Non-mammal, so that is correct. Okay. So I'm circling only those training set examples which are incorrectly labeled. So pigeon is fine, so we will not label it. Elephant, warm-blooded, yes. Four-legged, yes. Hibernates, okay, hibernate is not there. Okay, so I think all are correct, right? Warm-blooded, gives birth, and four-legged, so it is also correct. Leopard shark. So whenever any animal is cold-blooded, it is directly non-mammal. So I think all the cold-blooded are anyway non-mammal, so it is fine. So all of these are cold-blooded. So for all these, they will be correctly labeled as non-mammals. Fine. Let's come to the next. Dolphin. Warm-blooded. Gives birth. Yes. Four-legged. No. But it is a mammal, but here it is classifying it as non-mammal. Right? It is not four-legged. It is not a mammal. So there is one more problem here. What about the spiny anteater? That doesn't give birth. Whether it will be classified as a mammal or non-mammal. Spiny anteater. So it will be classified as non-mammal. Okay, because it doesn't give birth, so it will go to non-mammal. So it is also a problem. One more problem here. So it's an error. Last one is the monster, Gila monster. So it is cold-blooded. So it is not correct. It is correct, I guess. So there are 3 out of 10 are incorrectly labeled. 3 out of 10 from the first decision tree. Okay. Now suppose you have pruned the decision tree. So pruning here means combining, or you can say you can stop early. So you are kind of stopping here. Okay, I'll just write this down here. So the first one has given you 3 by 10, 3 out of 10 wrongs. Okay. So we remember. Okay, so when you are pruning, it means you are decreasing the complexity. Okay, so you start to create a decision tree, for example, and you might stop here. Instead of splitting further, you just stop here and say if the animal gives birth, then it's a mammal. Okay, so instead of this further splitting, you can see in the model M2, the bottom decision tree here, there's a single node instead of splitting further on four-legged. So here it is splitting on is not splitting on further. It's just saying if it gives birth, then it is a mammal. Okay. So now let's start again and look at the test set, but with a simpler or with a dispruned dysentery, and again start. So now let's see how many errors we are getting. The earlier one, the complex one, or the bigger dysentery gave us 3 out of 10 wrong. So let's start with human. So human warm blooded is right. Yes, gives birth is yes. So it is mammal. So it is correct. Human is correct. Pigeon warm blooded. Yes. Gives birth no. Non mammal is correct. Elephant warm blooded gives birth yes, correct. Leopard shark. So all the cold blooded animals will be correctly labeled. Now comes the dolphin. Warm blooded gives birth yes, and it is so it's correct, right? Spiny anteater. Warm blooded. Yes. Then gives birth no. So we're saying non-mammal. So spiny anteater is incorrectly labeled. Okay, spiny anteater is incorrectly labeled as non-mammal because gives birth is no there. And then Gila monster is correct. So I guess there's only one wrong, is it? So only 1 out of 10 is wrong. Okay, there's a comment. Leopard shark. Leopard shark is cold-blooded. Cold-blooded is no, it's correct. Leopard shark is correctly labeled because anyone starting with the root node, cold-blooded is strict non-mammal according to model M2. So that is correct. So only 1 out of 10 is wrong. Okay, so you can see that the accuracy on the simpler model, on the model M2, is better, 1 out of 10. Right, only 10% error. On the other hand, on the more complex C, they got 3 out of 10 wrong. Okay, because they try to fit too much to the training data. Okay, because it further tried to split 4-legged based upon 4-legged, and then everything went wrong. When it split further on 4-legged, it made a more complex tree, and then whatever was the training examples, it fit according to that. Okay, but it should have stopped there without splitting, and then it could have gotten better results. Okay, let's look at spiny anteater. Why it gave wrong class here, long label. Why it was incorrectly labeled spiny anteater. So in the earlier class, the model M2 or model M1, was it incorrectly labeled spiny anteater? So it is warm blooded. Gives birth was no, so it was non-mammal. Okay, so it is incorrectly labeled there also. Okay, so spiny anteater will anyway be incorrectly labeled. And now let's look at the training set. Okay, let's see what happens when body temperature is warm blooded and gives birth is no. Okay, that is what the case with the spiny anteater is. Okay, so spiny anteater is warm blooded and gives birth is no. So what happens in the training error in the training set? So warm blooded and with gives birth no. So here you can see there is only one example of eagle, right? When it was warm blooded and gives birth was no, right? And because it was no, the label was no, so it immediately said, because there is only one example, it said when this case comes in model M1 or model M2, in both cases, it will straightly go to no, label as no. Okay, so but in this case, actually spiny anteater has warm blooded. It doesn't give birth, but still it is a mammal. It is classified as a mammal. Okay, So this will anyway be in whatever model you give, it will be incorrectly classified because you don't have enough samples. Okay, now there's a question. Okay, so there's a question, but sir, four-legged itself is wrong attribute for classification. Okay, it could be. Okay, four-legged may not be a good feature. Okay, so that's why it's important to have good features in classification. Okay, that's fine. Okay, so there are just four features that have been picked up just for this example. We may improve upon this. Okay, in the real world, people might not use these four features, this four-legged feature. Okay, or if it is four-legged, may have some examples, some more features which will clearly distinguish among mammal and non-mammal. Okay, so some more features might be required too, or more samples might be required, or you might need to improve the training set such that the noise is less. Yes, so if you select wrong features, then obviously you will not be able to train well, right? Yes. Yeah, so that's why I'm repeating the questions. Whatever the students are asking, I'm repeating the questions. Okay. So anyway, so can you please all send to all participants whenever you are, just send to all participants. Select from the drop down all participants so that other can also see your question if it is possible. Okay. Otherwise, I'll just keep on repeating the question for others. Okay. So you can have, if you have wrong features or insufficient features, obviously your model will not be correct. Okay. So you should have good enough features. So that itself is feature engineering itself is a big topic. Okay, how to create features, how to select features, all these things. All right, so this one is saw the overfitting in the more complex tree. Okay, let's look at another example in which you have very less data. You don't have much training data. Okay, and you see again the same set of test sets, but the training set is now smaller. Okay, you don't have much samples or much examples to train or to learn the classification or learn the classifier. Okay, now based upon these 5 samples, you have created a decision tree that looks like this. Okay, so that is the root node is body temperature, and if it is cold-blooded, it is straight no. So if it is cold-blooded, it is straight no. Okay, and I guess in the test set also, if it is cold-blooded, it is straight no. So that's correct. Okay, so you don't have to look at the cold-blooded animals because for all the test and the training examples, they are no, and from the tree also it is straight forward classifying any cold-blooded animal as non-mammal. So what is cold-blooded animal anyway? Cold-blooded, what is meaning of that? So those animals which can actually alter their body temperature. Okay, so can human do that? Can human being alter their body temperature? No, right? That's why we are warm-blooded. Okay, so our body temperature remains fixed whether it is cold weather or whether it's hot weather, whatever, it remains fixed as around 37 degrees Celsius. So we are warm-blooded. Okay, and the cold-blooded animals, on the other hand, during winter they will bring down their temperature, body temperature, and during summer or during hot weather, they can increase their body temperature. Okay, like snakes. Okay, so here you can see apart from these cold-blooded, you have 3 samples for warm-blooded, and so let's look at those 3 samples. So first one is eagle, warm-blooded. Then the next feature is hibernate. Okay, so according to this training set, the tree created has second test is on hibernation, whether it hibernates or not. If it hibernates, if it doesn't hibernate, okay, if it doesn't hibernate, it says it is non-mammal. Doesn't hibernate. For warm-blooded animal, doesn't hibernate, it says it is a non-mammal. Because why did it say so? because there is only one sample, right? That is eagle in the training set, which corresponds to this particular features, this particular combination of features. Whereas where an eagle is warm-blooded, it doesn't hibernate, so it will be labeled. It is because it is labeled as no in the training set. So this particular combination will always label any living being with this characteristic, this combination, as non-mammal, such as human. Okay, human will also have this characteristic. It has body temperature, it is warm-blooded, it doesn't hibernate, so it will be incorrectly classified as non-mammal. Okay, whereas it should be classified as mammal. Okay, so because you don't have enough example, if there was some other example in which they were warm-blooded animal which don't hibernate and but which are labeled as mammal, in that case the decision tree would be split further, right? Here in this it would further split on non-mammal and would create a proper tree. Alright, but in this case, because there was not enough example, so it only fitted this particular case. Okay, next one is poor will. That is warm-blooded and hibernates. Okay, let's come here. Left side, hibernates. It's here. But then it comes to four-legged. It is more than non-mammal. Hibernates, and if it is not four-legged, is non-mammal because of this particular example. The example of poor will. Because of that example, it said if it is, it doesn't. If it hibernates, but it is not a four-legged, then it is not a mammal. Okay, so if a warm-blooded hibernating animal doesn't have four legs, then it is non-mammal. So according to this particular decision tree, a warm-blooded, four-legged animal or a warm-blooded hibernating animal must be four-legged, then only it will be a mammal. Okay, that is what it's saying. So you see that you can see that there will be a lot of mislabeling here, right? Okay, there is a question: why gives birth feature not used in decision tree? Okay, so remember that in decision tree not all features may be used. Okay, or maybe not be important enough. Okay, so body. So in this case, birth feature, according to this decision tree, I don't know what approach they have used, but sometimes it happens that you get enough examples. All the examples are of the same set, then you don't require further features. Okay, it might happen. Okay. Because the features here itself, they were able to fully fit into the training set. Okay, because the training set was small enough, and the Gibbs birth was not found important here. Okay, in this particular decision tree. Okay, so no, it is not. It is not a derivative feature, but so this question is derivative. So it is not a derivative feature. Okay, Gibbs birth is not a derivative feature. It's not deriving from any other feature. Right? It's not derived from any other feature, but there are not enough examples here basically. Okay, to make Gibbs birth an important one. Okay, so here you will have many misclassifications. So what are misclassified? You can see that human will be misclassified. So any warm-blooded animal who doesn't hibernate will be misclassified. So you can see that human, elephant, wrong. Okay, dolphin is wrong. So there are three wrongs just based upon warm-blooded and not hibernating animals. Any other sample which is wrongly labeled or in the test set? What about pigeon? Warm-blooded, doesn't hibernate, so it is correct, right? Leopard shark, okay, cold-blooded are all fine, right? Cold-blooded are all fine. Yeah. is spiny anteater, warm-blooded, hibernates, four-legged. It's correct. It's fine. So they are 3 out of 10 incorrectly classified. Alright, and all 3 were warm-blooded who don't hibernate. Okay, so perhaps we had some more examples of in the training set in which we have warm-blooded animals who don't hibernate but which are mammals. Then you would have got some correct labels. Okay, so this is a forfeiting because it is fitting too much because in the training set itself is insufficient. Okay, so basically. Alright, so one thing that you will be doing in the assignment also, if you are doing doing that problem of classification using decision trees, something called pruning. Okay. So pre-pruning basically you will be performing, not post-pruning. So we'll discuss the assignment later on. Okay, don't worry about that. Okay, example. So in case of post-pruning, you first create a decision tree. Okay, and then you start combining leaf nodes. Okay, until the cross validation error is minimum, until the error on the validation set is minimized. Okay, so you'll see whether a particular, when you clump together a particular set of leaf nodes to create a single node, whether that is improving your accuracy, okay, or the error is decreasing. So as long as the error keeps on decreasing on the validation set, you will keep on combining leaf nodes into a bigger node. Okay, and you'll keep on doing this until the desired level of accuracy is achieved. Okay, or until the error keeps on decreasing. So if beyond a level, when you start combining those leaf nodes to into bigger nodes, if the error starts increasing beyond that, then you stop there. Okay, you say that now your tree is complete, your tree is properly pruned. So you first create a complete tree and then do post pruning. Okay, so this is available in some of the software, not in SKLearn. Okay, in SKLearn you don't have post pruning available, but what you have available is early stopping. Okay, in early stopping, what you do is you just start creating decision tree splitting, and then you stop sometime. You will stop at a point when maybe the decrease in the entropy, for example, if you are using entropy or Gini, whatever you are using, if that is not decreasing beyond some point, okay, then you will stop. You will not do a further split. Okay, maybe you decided, okay, the node will be split only when the entropy decreases by at least, let's say, 0.001. Okay, if it is decreasing beyond that, then only you will split. If it is not decreasing enough, just stop. Don't split. So you may decide that, or you may decide that, okay, if the number of samples in a particular in a particular level reaches some number, then you will not split further. Okay, or might in SKLearn you also have an example in which okay, so in some cases you just say whether to split. After splitting, if each of the two nodes on which you are splitting, if each of them should have at least this many members, then only it will split, otherwise it won't split. Okay. So there are multiple features you'll see if you look at the decision tree classifier in SKLearn. There are a lot of parameters that you can set for early stopping or pre-pruning. Okay. Other examples is and so you'll keep on you can prune or pre-prune based upon that. Okay, now there's a question. Okay, here all features are yes or no, but in our assignment not so. Yes, it is true. In the assignment, the features are numeric. Okay, but that's fine. Okay, they are numeric features. So as long as you are not getting multiple what you call categorical features, right? More than binary. If you're not having categorical features which are not binary, then you have problem. Then you might have to create dummy variables. But if the features are numeric, then you don't have to worry. Only for such cases, only you have to worry about such cases when categorical features have more than two values. Can have more than two values apart from binary categorical variables. Then you need to create dummy variables. Okay. In your assignment, they are numeric features. All the features, because text features are all numeric. All right. Okay. Another question is: can Python provide solution automatically, or we need to work on this pruning? You need to work upon this. Okay. You need to work on the pruning or whatever, or list stopping. So let's try with different arguments, different numbers, different values for the arguments, and see which is giving you the best result. Okay. So that is about pruning the decision tree. And one small topic that I will just spend 1 or 2 minutes is ensemble methods. Okay, there is a question: is there a formula for pruning? No, there is no formula for pruning. Okay, you just prune it and then test it. As long as your accuracy is improving, keep on doing that. Okay, so look at the validation set or your result and select the one which is giving good results. That's all. So it's all trial and error. So a lot of machine learning is trial and error. Okay, just look at the output and select the one which is giving best result. Okay, so we're not going to detail of overfitting and underfitting. It's a very vast topic, but you have got an idea, right? So that's all that is required. You want to learn more about overfitting or underfitting? There are a lot of literature available online. In machine learning, it's a very big topic. In data mining also, it might be present. Okay, a very common example in overfitting is given like this. Let's say these are some samples, and you want to classify these samples. Okay, let's say these are some space in the space. These are some samples which are there. Okay, now there might be a very complex classifier which creates the classifier boundary such as this. Might create a boundary like this. Let's say let's start from here and then finds it. Okay, here it is. The red is there, so it's kind of trying to fit. It's trying to put. Oh, sorry. It's trying to put all the blue points above the red points. Okay, so it will try maybe something like this. Okay, so all the blue points above the red point, something like this. So it's very complex. Okay. Okay, so you might learn something like this. Okay, so here it is trying to fit everything too much to the training set. Okay, rather than let's have some not. So here what is happening? The training error is very good, right? You are not getting any error in the training set. So rather, if you just I think I missed everything. Okay, let's draw one more similar kind of drawing. Some interspersed different classes. So here blue and red classes are different. Okay, so there's red somewhere here. Most of them are downwards, but there are some red points which are kind of closer to blue. Okay, and another simple classifier, it might create a simpler boundary, decision boundary. Okay, so in this case, in the training set, it is getting good results. But what can happen is that the test set will give good results. Okay, simpler one is giving good results. So it is not fitting too much to the training set. Okay, overfitting small confusion. Please type your confusion. Okay, till then we will just start. Spend a couple of minutes on ensemble methods. So these are the methods. What happen in these methods? Okay, we'll take a small break this time, and then we'll continue the ensemble methods. So these are only a couple of slides of this, and then we'll go on to discuss the assignments. Okay. So let's stop here and take a small 5-minute break.